Bam, Mr. True. In this video, we're going to be talking about working through the chi-square test calculation by hand. I had a couple of requests from students whose teachers were forcing them to go through these problems by hand as opposed to just allowing the calculator to do all the work for them. So, it's awfully mean, maybe just one time with a small set of data, but I wouldn't want my kids to have to do that every single test. So I went through my old examples and I found the example that had the smallest table, the smallest number of cells in the table, and we're going to revisit that example. If you'd like to see the full video, I've got the link here above the chalkboard. Please go check it out because we are going to be just emphasizing the hand calculations in this video. So H sub O is, there is no association between gender and snacking, or there is an association between gender and snacking. This language for H sub O and H sub A will be appropriate if, when you read your problem you're going to work on, if it states that there's only one SRS. You know, you took a simple random sample of individuals, you then broke up their gender based on their snacking habits, and you're analyzing the data. If it states that there was an SRS of males and a separate SRS for females, then H sub O is going to be the proportion of snacking are equal between genders, and H sub A is the proportion of snacking are not going to be equal. So let's get this board cleared off, get the data up here, and run through the calculation by hand as opposed to being dependent on the calculator. Bam! So, we have our two-way table showing that we had 231 men say yes they snacked and 149 thus saying they don't. We have 196 females saying yes and 174 saying they don't. Okay, so we have our observed count values. Now to figure out chi-square, which is the sum of the observed minus expected squared divided by the expected. That means we're going to do a subtraction, we're going to square, we're going to take that answer, divide it by E. We're going to do that for every single one of the cells in the table, and since we have 4, we're going to have 4 terms in this calculation. And then the summation symbol says just go back and add them all up. Degree of freedom in a two-way table is the number of rows minus 1 times the number of columns minus 1. Now, if this were a one-way table, then we would still be using the same formula. There is only one chi-square formula that we're studying, and the degree of freedom would be the number of cells in the table minus 1. So if you had 7 numbers in a one-way table, 7 cells, then the degree of freedom would be 7 minus 1, or 6. Okay, so we need to calculate the expected cell counts from these observed cell counts. And in a two-way table, your expected cell count is row total times column total divided by the total number of observations that we see in our two-way table. If this were a one-way table, a one-way distribution, we would have a population distribution basically given to us in the problem, and we could just take those percents that are stated in that description of the population and just multiply that percentage to the total number of observations made, and you can find all your expected cell counts. But for a two-way table, it's row total times column total divided by, I like to say, total. So, for the first row, first column, we have 231 as what we observed. To calculate the expected cell count, we would add those numbers in the row. Again, this would be the first cell in the first row. Add those up, you get 427. And the 231 is in column 1, the total for that is 380. We're going to multiply that and divide that by all the observations that are in the two-way table, and I've already done that for us, it's 750. Now we're going to do it for the nose, so we have, this is going to be the second row, first column, so the sum of the second row is at 323. The column total is again 380. And then we're going to divide by the total of the table again, which is 750. And then move on to the second column. Row 1, second column, that's going to be this cell right here, the 196 observed. What were we expecting if there was no association between gender and snacking habits, or if the proportions were equal? Well, that would be 427 times the sum of that column, which is 370, divided by, again, the 750, And finally, the last cell here, second row, second column, the sum of that is 323. Column total again, 370 over 750. Now I'm leaving some extra space because I don't have room to write a whole new matrix. Of course, I guess I could have squeezed it over here, but I'm just going to put the answers next to these calculations for you. And let's just do that in a different color, white, so it's easier to see. And we get some expected cell counts of 216.3 and 163.7, 210.7, and 159.3. Okay, now remember, H sub O is no association or or that the proportions between the snacking habits between men and women are equal. So if that was true, then these are the expected cell counts that we should have gotten, or we were expecting, based on H sub O, which we are assuming to be true. So we have observed, we have expected, we have a formula to work through, so let's do that. So we're going to have the chi-square is equal to the summation of the observed minus expected. Now, it doesn't really matter what order you do this in. I'm going to follow my notes and go straight across and then down, like I'm reading a book. Only, yes. So 231 minus my expected of 216 squared divided by my expected value of 216.3. Now let's move on to the next cell in the table, which is 196. So observed again, minus expected, squared, divided by expected. That is a point there. Moving on to the next one, 149. So we have plus 149 minus 163.7 squared divided by 163.7, and finally the 174, the last cell we have to deal with, which is going to be our last observed value minus the expected value squared over 159.3. That gives us 4 elements, 4, terms here. 1, 2, 3, 4. Those come out to be, I think I can squeeze it in here. 1, now this is round off a little bit. So 1 plus 1.03 plus 1.32 plus 1.356. To compare these numbers to my full-blown video where I have the calculator do all this work, the numbers are going to vary a little bit because of round-off error. That gives me a chi-square value after I add up these 4 terms, and by the way, clearly this is the biggest term, so that's going to be the term, the female saying they don't snack. That's going to be the element that, gives us the biggest hit to our chi-square value, that increases it the most. If that may be necessary, sometimes that's asked for in the book, which element, which term had the biggest impact on chi-square, which one made it grow the most. So our chi-square value comes out to be, drum roll please, 4.71, which, with a degree of freedom, which is rows minus 1, so 2 minus 1, times column minus 1, or a degree of freedom of 1, we get a chi-square value, we already have that. We have a p-value that is between 0.025 and 0.05. So we have, with our p-value between 2.5 and 5%, we have some evidence that the snacking habits between the genders, male and female, are associated, the snacking habits are different, the proportions are not equal. whatever summary statement you'd like, you need to tie that summary statement into how you set up H sub O. If H sub O and H sub A, if H sub O is no association, then H sub A is there is an association. There's some evidence for H sub A that there is an association. Or the proportions are equal, the proportions are not equal. We have evidence that the proportions are not equal. Now, if we've concluded that there's some evidence that the proportion of snacking, the habits are different between men and women, it might be nice to talk about those. I've done that in a full-blown video, but let me just quickly verbalize it. We are expecting the gender of the person to help explain whether or not they snack. I mean, that seems like gender would be the explanatory variable. I don't think whether or not I guess you could argue that you could look at snacking habits and guesstimate if they're male or female. But to me, it makes more sense to say that the gender is the explanatory variable. So if you wanted to talk more about what that association is, then you would want to find some column percents between those two genders. 231 divided by 380 is blank. 196 divided by 370 is blank. And here you can see that, I think I actually have those numbers, that the female snacking rate is 53%, whereas the male snacking rate is 60.7%. So I'm Mr. True, and that's your example of how to do chi-square by hand if your teacher's making you do that over and over again. Bye! Go do your homework.